Sejam bem-vindos ao nosso seminário semanal do Laboratório Graf, em Computação Gráfica. Hoje nós estamos dando prosseguimento aí ao ciclo de palestras do nosso evento de Computação, Música e Matemática. Então, o Pablo Riera, que é o físico formado na Universidade de Buenos Aires, é nosso colaborador aqui do laboratório desde o ano passado, já vem visitando o IMPA. Ele vai fazer a terceira palestra, então, do nosso ciclo de palestras. Então, eu passo a palavra para o Pablo.
Oi, boa tarde a todos. Muito agradecido a Victor pelo convite, ao professor Luiz também. Mas em português fica aqui. So now I was talking English. Maybe it's easier for me to share this talk. So I will talk about a collection of examples and some expertise on some stuff that I have been using to teach math to music students. So I will describe a little bit of this course I give, and then I will show some examples. Hopefully, if everything works okay, because there are going to be some live examples using math to create music. So, well, of my background, I'm working right now in the Artificial Intelligence Lab in University of Buenos Aires. But I studied physics and acoustics and some music also. And whenever I have the chance, I try to combine both. So I have been giving this course in the University Nacional of Quilmes, which is in Argentina, near Buenos Aires, where there are 2 music degrees there, and there is this course that is called Math Applied to Music, where the students are from the last year, so they know a lot of music and music technology also, but they are not very skilled on math or programming. So it's really interesting and challenging to explain some complex math problems or programming problems. So through the years, I developed a combination of examples that, well, now you will listen in a few moments. The main thing is try to create concepts by listening or understand concepts. So if anyone wants to follow the talk in slides, there is a version of the talk here in this website. It's not the same, but it's from yesterday. So this course has a lot of topics. They are not all equally seen in deep, but in the course we discuss numbers, sequences, functions, calculus, and mainly Fourier Analysis. That is the main tool for musicians to use to understand music. Also some signal processing, digital filters, and I try to put some more advanced topics like physical modeling of sound and some probability theory to generate music, algorithmic music. So, as I said, these are math or physics or engineering topics. They have difficult concepts to understand for musicians. So the thing is, let's make it sound. That's the theme of the course. So, this is just something related to the programming part. We use Python and live coding tools also. So the thing is to use this concept of sonification, which is a very old concept. there are some books from the 80s about this. There are some really famous examples of how to use sound to understand data. For example, the Geiger counter for radioactivity. You are not watching the numbers, you are listening to the counts. Or in neuroscience, there are also, they use sound to listen to neurons fire instead of seeing it, because you can put your eyes in another place while you listen. So it's a really interesting topic. So here we'll base on this idea of creating sound with data, patterns, and stuff to understand mathematical concepts or engineering concepts. So first example of sonification, I will show some code sometimes. So this is Python. This is the type of tools we use in the class. So the students have computers with this type of interface present, so they can change the code and execute it and have scores and sounds. So for example, here we will listen to this sequence of integers. As a basic example, it's just will be the notes in a scale, starting by 0, the first note in the scale. In this case, this will be the major scale of C. That you can change it if you want. So if you define that sequence of numbers and you generate this sequence, you get this result. Yes, it's. Let me see if I can get a little more of this. So pretty straightforward. Is if any has a question about how, because we are going to see a lot of these sets of numbers or definitions transform into sound. If anyone has questions about how it's done, please interrupt. It's okay. So this is like the basic example, but we can generate more complex examples. For example, something we are going to see in the following slides also is a harmonic series of frequencies. If you take one fundamental frequency and you multiply by natural numbers, you get a set of frequencies that are in harmonic relation. So here I have a list of numbers. I will define that the base frequency is 440, which is the A, the middle A. And then we transform this set of frequencies to a set of notes that are in a standard format. And we can generate the score and listen to it. So for musicians, this is well known. So maybe, I don't know if there are any musicians here, they are familiar with it. One interesting thing is that these notes, the notes from the first example, are in a scale, and they are well tuned. They are tempered to the 12-note system. But the notes in the second example, they have not a fixed tuning. They are natural harmonics. Good. Second example about sonification will be not generating scores or musical notes sequences, but rather waveforms. So in this example, it is pretty straightforward also. This is the basic thing we are generating there. It's a sine wave with a definited frequency, fixed frequency, and evolving in time, oscillating in time. So we can generate here a waveform. We will see in next slides something more complex about this. But we can draw it and listen to it. So it's clippings. That's why it sounded not sine wavely, but there is a little bit of clipping there, but okay, it's okay. So this is basically the two types of sonification we're going to use. Any question, please ask. So one is sets of numbers to sets of notes, and the other is more large sets of numbers, like arrays of numbers to waveforms. Yes. So and one little more example is this is just the same. Instead of a sine wave, it is a noise. So to generate this is just a sequence of random numbers that it sounds like noise. And this is really interesting because if you listen to some sound and you heard and you notice this is noisy, you can probably make a correspondence with the nature of the sequence of numbers that has some randomness on it. So it's not a proof of anything that is random, but it's like a conceptualization by listening. Okay, and then also we have this tool that is really interesting because it's the same methodology I described there to write functions to generate sine waves, but with the advantage of being can be visualized in real time, and it's a live coding interface. So here has also clipping. I will make it there. So we can put some noise, and it's really useful because you can see the waveform moving. And the only difference is that here the time, the t variable has different units, so it's normalized to sound in a note. Okay, so first example, yes?
In that format, you can change the sign of t to anything that two notes sound at the same time.
Yes, if you, good question. If you add here 2 times t, it will sound the octave, yes, 2 times higher. And you can put here any fraction or whatever. And this is very flexible. You can define variables and start creating complex waveforms. If anyone wants to check this is the website of this tool. Otherwise, you can ask me later. So now I will show some examples of how to explain some properties of numbers to musicians, and hopefully most people here are familiar with these topics, but sometimes some concepts appear differently by listening. So this is the problem I want to study first, is how are harmonics in string organized. I will show an example. So if you do that with string, in this case a cello, you slide your finger over the string, you will force some parts of the string not to move, to be notes of the modes of vibration, and depending where is your finger, a different note will sound. So this is a common technique that musicians do, the sliding of harmonic sliding. So the musicians are really familiar with this, but they don't know exactly how to compute the sequence of notes that appear when you slide your finger linearly, for example. So this is something most musicians are also familiar with, and mathematicians also, is the modes of vibration of a string. So we have the fundamental note in the first case, then the first harmonic or second harmonic, depending how we count, third, fourth, and so on. And the question we want to know is, I know it seems clearly, we want to know how are these harmonics ordered. So if this is the string, and we move the finger over the string, when we push our finger here, we will excite this harmonic because we will put a node here with our finger, and then we will move our finger, so this note will sound. And the notes here are in a harmonic series that we listened before. So the first one is the fundamental. The second harmonic has the double frequency, third frequency, and so on. So we want to know the order of these notes, okay? So if we follow this example just by doing it with this figure, we see, okay, this is the 7th harmonic first, then the 6th harmonic, then the 5th harmonic, then the 4th harmonic, then we go back to the 7th. So the scale will sound 7, 6, 5, 4, 7, 3, and so on. So we want to generate this sequence that mathematically, or mathematicians know these sequences for a long time. It's called the Fourier sequence, Fourier, or Fourier, I don't know how to pronounce it. But if we want to simulate that we are moving our finger over the string, we would like to note for a given position which is the closest harmonic that is sounding. For example, if we set a bound to upper bound to the harmonic, so for example, we say, okay, we have only 7 harmonics. So we have these 7 harmonics, and I put the finger here. Okay, we get the second harmonic. But if I put the finger all over this place, I will get the same harmonic. Okay, if someone is familiar with guitar, this is what it happens. If you put your finger here, you will excite that harmonic, but you can put also your finger near this area, and it will sound the same. So this is a way of describing the problem. We want, given a real number and a maximum numbers of harmonics, an upper bound, we want a rational number k over n that approximates x with the lowest n. So we can solve this problem with an algorithm. And for example, if we set the maximum harmonic we want is 9, so 1/2 is 1/2, but 1/10 is 1/9, okay? And this is 1/17, 1/7, sorry. So now we are going to do this, but for all the position in the string. So I will say, okay, I have a string that goes from 0 to 1 with a lot of small steps, and I want to find which is the rational number that is approximated. But what I want is this, the denominator. This is the harmonic, because if we remember this is the 7th harmonic, but this is 1/7, this is 2/7, 3/7, but the important thing is that it's the 7, the denominator of the rational number. So if we plot how is the harmonic number related to the position in the string, we have this sequence that we can hear now because we know how to transform sequence of numbers to notes with the tool I showed before. So this is how it sounds. We have to define a base frequency. So, okay, the string will, if we play it freely, it will sound like an A, A2. And then we will have the harmonics related to that note. Okay, so that is more or less what would happen if you slide your finger slowly over the string. Here, for example, the durations of the note are related to how much length they stay here. For example, this note will only sound just a smaller time than this, because they have more region in the string. And so, as I mentioned, this sequence is in mathematics called the Faraday sequence. So there are many examples of this. Even in music, there are a lot of examples of using this sequence. So, for example, the Faraday 9 sequence is this. It's 0, 1, 9, 1, 8, 7, 1, 6, 1, 2, 9, and so on. And it's usually depicted like this, like a grid, and it has the same pattern we saw before. And now I will take some music liberty to generate something more interesting, maybe, because if we have a high span of frequencies, maybe it's nicer to have two different instruments, one for the low note and one for the higher notes. So the first four notes, harmonics will sound a trombone, and in the higher part will sound a guitar. And I will repeat this several times. No? So it's in terms of code, the code to generate that is not that much. It's just a little bit of code. So it's really easy to change instruments, for example. So if you want to segregate patterns by listening. So now let's go to try something more extreme. This is the Faraday 96 sequence that I put the lowest note is the lowest note in the piano. So this could actually can be played in a piano, but it's difficult because you have to. But they are yes. It says Faraday 96, but there are no 96 notes because some notes repeat. Because in the piano we have fixed notes, so many of these sound the same. But because a typical piano has 88 notes, but this can be played in a piano. And there is a very famous composer called Colon Nauncarro from the first part of the last century that used to generate this type of compositions that are not played by humans, rather by a machine, a pianola. So let's try to listen this. And maybe you can grasp what is, visually you see some patterns that go up and some other patterns that go down. Okay, visually it's easy, but let's see if you can pick that up by the ear, with the ear. If you listen it for several times, you will see some. You get familiar with the the melodies that appear. But okay, it's most of the rest of the fragment sounds mostly the same. But it's really interesting because it's symmetric. So if you listen to this without seeing the figure, you probably will listen that it's symmetric. So it will start some way and would end in the same way. So next, well, here are some reference to if anyone wants to dig into this. There is actually a very interesting series of papers about the Fourier series and music that were worked out in these years. And there is also one great piece from Ligeti that uses the Devil staircase, that is a pattern related to the Fourier series. So there is much been done in this topic in math and music. So now I will move on to irrational numbers, because, well, in a sense, what we saw in those slides was about rational numbers and how they are organized. And now to the students, I ask the question, what about irrational numbers? And nobody knows much about that. We know that there are many irrational numbers and that the digits are distributed somehow randomly, probably. So we start with pi. So we take a file with 1,000,000 of digits of pi. Here is just a small piece, and we are going to make a sonification of pi. That is a problem that is, or a thing that is done, has been done many times. If you search in YouTube pi music, you have tons of videos with different approaches to create music with this. So the first one, the most simpler, is to make a mapping between the notes, the numbers and the notes of pi. So here we have a fixed scale, is C major. Scale is the white keys in the piano. So the third note here is F. This is D, the first note. So this is 3, 1, 4, 1, 5, 9. So there are the digits of pi. If we listen to this, it appears that maybe for someone there is like something going on. It's okay, I have some melody that ended and started another melody, and it's like something there that is not completely random, but we know it's random. So if we listen to infinite numbers of pi like this, eventually we'll hear all the melodies possible. So this is a nice way to describe irrational numbers to musicians by listening to melodies. So, and in this case was really simple because we only have 10 notes, and all the notes have the same duration. So it's really easy to listen to, but we can create more complex examples. But the thing now is, if I want to listen to many more digits, listening notes like that is going to take a long time. So we move to a waveform. So now the digits of pi are here in a waveform. So this is 3, 1, 4, 1, 5, 9, so on. So if depending how much fast we create sound with these digits, we can listen to a lot of digits. So in this example, the audio lasts 20 seconds and has 1 million digits, approximately. So if we listen to this, what do we get? It's noise. And probably if we keep listening to this for a long time, it will be always the same. So it's a non-mathematical proof that there is not structure in pi, just by listening to it. And as I said, if what we hear is noise, it's probably because there is randomness there. And maybe if people is not familiar to listening noise, they would say, okay, how could I know? But it's really interesting because if you start removing the randomness slightly from the noise, you start listening changes. The high frequencies tend to diminish. So in a sense, if your ears are really calibrated to listen to white noise, you can make a diagnosis that it is random. Now, more complex examples of sonification. This is really something I don't understand it well. If there is someone expert in number theory, it would be nice to have some discussion about this. But maybe there are somewhat. I believe everybody in a time wonders about the prime numbers, or how are the numbers like that? 1, 2, 3. Why are they like that and not differently? So a way to understand that is by computing some complex function. For example, the divisor function is a function that, given a natural number n, gives you how many divisors the number has. Or there is another function that can give you the number of distinct prime factors of a number. There are many functions that, in a way, describe a number. Or where is that number? For example, the distance to the next prime gives you, from a given number is how far is to the next prime. And we can also study the prime gap, that is the distance between consecutive primes. So all of these functions are really well studied in the mathematics. They all tend to increase in value because higher numbers have higher values of number of divisors or number of distinct prime factors and so on. So if you want to listen to this, we have a function that increases in time. If we consider that time are the natural numbers, we have a function that increases time. So we want to normalize it somehow to make it bounded. So we perform that normalization. So let's try to listen this. So we have all these functions I mentioned. We have a sound corresponding to it. And this is really interesting. Let me see if the sound is OK. OK, so that was the normalized divisor function. So instead of the sound that we got while we listened pi, that was randomness and noisy, here we definitely listen to something with more musical structure. There are a collection of notes in the sound, making a chord. A chord is so the other functions have similar sounds also. Has less we have notes, but also noise. Here we have less noise. And now these functions have some information about the prime numbers, but also have information about all the numbers. But the following functions are more related to the prime numbers. So the distance to the next prime number or the prime gap is, I believe, I'm not an expert, that is probably have some randomness in there because we don't know how to compute the next prime. So it's mostly noise, but filtered noise, so it's not completely random because the distance to the next prime has a correlation because the following number is the same, -1. If not, it's not a prime. But the prime gap is probably random. But sometimes you have a long shot to the next prime, or sometimes you have a really close primes. So this is really interesting for me to listen to this because otherwise you can't make a visualization of these functions. But you can listen this for a long time to see if something appears there. So, yes.
Haven't you considered to filter the low frequencies, like ignoring other numbers with low?
That would be nice to listen clearly what is happening in the high frequencies. I didn't manipulate much this sound, but what I did is a spectral analysis that is we're going to see right now. I will show the spectrum is this. So this is the spectrum of the first sound we heard, the divisor function sound. And we can see this is the spectrum. The frequency scale is not a linear or logarithmic scale. It's a different scale just made to visualize the pattern in a symmetric way. And the red lines are there to mark the highest notes. So that are the notes we are listening when we hear this. And they follow this simple law. They are all the divisors of one number, that in this case is the number of the frequency rate we are putting all the numbers through the waveform. So if we take these red lines and transform it to notes, for example, this line is 1,500 hertz. That's one note. This is 1,000 hertz, and so on. We can make a chord of notes. So now we will not have all the noise sound. We'll just have the specific notes. And we can see something similar to that function. But for example, the tuning of those notes is not tempered. You cannot play those exact notes in a piano. But if we round a little bit of the frequencies, we can create a chord that we can play it actually in an instrument. And it's a really nice chord. I know, I like it. Maybe it has some tension. Maybe one day we will have some music made with this. Why not? So now I will change subject. Any question so far with something? Please stop. It's okay. Now I will change to another subject that is really interesting for musicians to understand. That is modular arithmetics and phase. What I mean phase is the phase of a periodic function or phase space. So in music, there are lots of examples where this happens. first we will see a classic situation that is this circle of notes. So most musicians are familiar with this, but they don't know that they have a lot of mathematical properties. These are really well studied from many years now. They have the notes. If you create a set of notes, you have group properties like translation or transposition, inversion, and so on. And I'm not an expert in this field. There are many books about this. I will only show one example of something that is really common in music, that is the circle of fifth, that in terms of the 12 notes, a fifth is moving 7 semitones, seven of these notes. That if someone doesn't know music, it's really confusing because it's a fifth, but it's 7. Okay, I'm sorry there. Musicians use numbers in different situations. When you have a 7-note scale, it's a fifth, but if we have 12 notes, it's a 7. So I will move from 0 to 7, and then I will keep adding 7 in this circle. So 14 is going to be 2, and so on. So in code, this is really simple. We just create a sequence of nodes jumping 7 by 7, and then we add modulo 12 operation, and we are good. So that's it. That's the circle of fifth. Not so interesting. But now we can create a different scenario. And instead of having the 12 notes that are all the notes in Western music, we will create a set of 7 notes. So it's going to be a measure scale, 7 notes in the measure scale. And now we're going to do the same. Instead of having a 12-note circle, we have a 7-note circle. And instead of using 1 note, we're going to use 4 notes to make a chord. So the first chord will be 0, 2, 4, 6. In music theory, there are a lot of work in treating chords like this. It's called pitch class set. So every one of these is a set of notes. So the first one is 0, 2, 4, 6, and then we're going to add 3 to every note. So 0 is 3, 2 is 5, 4 is 0, because it's 7. We are in modulo 7. 6 is 2, and so on. So we are adding 3, yes? We are moving 3 notes. That's only what we are going to do. But at the end, I will put the first chord. We are breaking the rule there. So if we listen to this, we generate a classic music progression that appears in many songs. So maybe the notes are not in the best form. They're very tight, but if you harmonize a little bit more, this is a classic song progression. So here the scale was A minor. So it's really interesting because many musicians already know this intuitively. They know that the notes repeat. There is a circularity there, but it's nice to see the math behind that. Now, well, here's some reference about group theory in music. This book particularly has all the topics I'm talking about and many more are in that book. And now, more examples. In this case, about phase. Musicians know a lot about phase because they have the the following situation. When they record music, they put microphones, many microphones, maybe in a piano or in a drum set. And if you have a same sound arriving 2 microphones that add different length from the sound, and then the sine wave, the waveform, sorry, that you took from those microphones, you sum it up. If there is a phase problem, you can get cancellations of the sound. Basically, when one wave is going up, the other wave is going down, you have a subtractive interference. So musicians know a lot of that. They tend to see the waveforms and try to slightly move everything so they don't get phase cancellations. They have a special button to avoid that in the mixers. So they also know that, for example, here I'm describing a simple sine wave. If you add a phase to the sine wave, for example, here, if I add plus it will sound the same. I'm going to show you that. But for now, the thing is, OK, they know something about phase, but let's create some frequency modulation. That's something a little bit more complicated. So to start, this is sound wave without frequency modulation, a constant frequency. It's exactly this formula here, and this is the spectrogram of the sine wave. I'm going to use some spectrograms now. So this is frequency, and this is time. We have only one frequency in time, straight. And the color is the intensity, so the white part is sounds louder. So now I asked to the students, how can we have some modulation frequency? Frequency modulation, if we want to make a siren sound, for example, doo. So the frequency we have to move, maybe also in a sine wave. So most of students, they say, OK, if I have the frequency definition here, I have a constant frequency, and then I want to add some modulation on top. So they write this. 40, 40, for 40 to 20 sine wave, 1 hertz, to make it something like that. And then the same formula from before. And this is, if we put this exactly in the formula, in the code, exactly like this, it's the same here. This is how it sounds. So, OK, the frequency is changing, but it's not what we wanted. We wanted something that has a siren sound. This was most like I don't know what thing sounds like that. So the problem is here is that the modulation we wanted was in the frequency. We want that, but we modulated the phase. So the thing is, you have to know a little bit of calculus to understand the problem, because phase and frequency are, in a general case, related by this formula. One is the derivative of the other. So this is a good point for musicians to learn the calculus, because you can say, well, we often teach calculus to young people by saying that velocity is the derivative of position in time, and you know velocity because it's physics and position. But here is interesting because we can talk about frequency being the velocity of phase. So it's circular motion. It's nothing strange, but for musicians this is interesting because they say, OK, if the phase of an oscillation goes faster, the frequency is increasing. So what we wanted is to generate a modulation in frequency, so now we have this formula. So it's easier. We put the frequency definition here, and we integrate this, and that's the solution. But you can imagine musicians don't know how to make integrals. So what we do is to make them use the Python like this. So it's an integrate, that's it. They don't know how it works behind. But this is the code that has the integral. And here it's just a normalization, so now we can put it in this system. So if we wanted that, we have to do all these calculations. There is no escape. There is no way of guessing, oh, I want this sound, I will hack the equation. You have to make an integral. So this is really tough to explain to musicians, but with these examples it's easier. And then what is interesting is now we have this formula allow us to generate a phase in time from any frequency in time. So frequency in time, we often call it instantaneous frequency because it's the frequency we want for any given time. So we can generate more complex sounds. For example, we can imagine whatever frequency in time we want. So if we want a stochastic frequency or whatever shape we want in frequency, we can generate it. And then to generate the sound, we have to make an integral. In this case, it's a numeric integral. It's not a symbolic one. And this sounds like this. It's really interesting. I know now you will tell me what you hear here. I don't know why, but it sounds like a cat, probably, or some animal. I made a little some tricks here to make it sound like that. There are many harmonics in the sound, so they are all in the same relation. That one is the fundamental, then multiplied by 2, by 3, by 4. But to make the sound, the cat sound, we have the loudest harmonic to be the ones here. You see the brightest ones. So this is really fun because we spend a lot of time generating signals with arbitrary frequency modulations, and you can make a lot of sonification with this. For example, I don't know, I want to hear how is the inflation in Argentina through the years. So you will hear something like that. Or whatever pattern of, you want to hear the temperature of the planet. You will hear it's going up, down, but sometimes it goes even higher. So, what? Yes. But it's not always the same result. If we run it again, for example, we can have something that goes in the direction. And that when it goes down, it's not so animal. OK, so now one last example about Fourier analysis and also phase. And this is also really interesting because this is actually something that is really being studied today. Fourier analysis it has a long time, but if we see this formula, this is the discrete Fourier transform, we see that the result of the transformation is a complex number that has two terms, of course, the absolute value m and the phase. Well, mathematician would say angle, probably, because it's an angle, but musicians would say phase, or engineers. So this is the phase, this is the magnitude in terms of spectral analysis of sound. Most of probably yes, all works in the literature that use some kind of Fourier analysis use the magnitude. The phase is has been left behind for many time. Now we have just in the last decade a new field that is called phase reconstruction. We have journals about phase reconstruction. There are a lot of things going about right now about the phase because in somehow the magnitude problem is already understood to generate sound or to analyze sound. The magnitude is okay. We already know how it works, but the phase is still, there are a lot of problems there. And the thing is that, for example, for sound synthesis, nowadays we have a lot of great applications that can talk really well today. They are starting to use the phase information to make more real sound. So the thing is, I will analyze. I will start with I am loading a song, a file. So this is something we do all the time. Also, we load a file, a WAV file or MP3 or whatever. So this is a Chico Buarque song, but made with a 8-bit sound. I thought it was appropriate because it has a clear rhythm, and the sounds are clear also. It's not a live recording or something like that. And this is just a visualization of the waveform, a portion of time. So we can see there is a lot of structure there. We have, this is a note because it has a clear oscillation. That pattern over there is probably something percussive because it has more fast oscillations. Probably the drum, and then we're going to first make a magnitude spectrogram. So this is the spectrogram. Probably many who use sound, work with sound already understand this because we have frequencies in time with different amplitudes. So in terms of the discrete Fourier transform, each one of these rows is a frequency component with a definite frequency that changes its amplitude in time, and that's it. But we can also see the phase spectrogram that is not so much used because it's not so easy to understand. But what we are seeing here now is in black is the part of the spectrum that are softer, quieter, that don't sound, and the color ones are the ones that are higher. But the interesting thing is that if we start moving in one row, in one fixed frequency, we will see the change in color. And this color palette is circular, so it works easy to visualize phase. To visualize, yes, the phase. So I don't know why, but this you can see some like snake pattern here, probably. This always something like that appears. I don't know if this is well studied. Probably yes. But now what we're going to do with this is, okay, now we have magnitude and phase separated. The Fourier transform is a linear process, so it has an inverse. So this is done a lot. You take a sound, you make the Fourier transform, and then you create the inverse. So you go back to sound. And in the Fourier space, you can make a lot of process. You can make equalization, change the frequency amplitude, or a lot of different process. This is known for a long time. But we can also perturbate the phase. That is also known, but there are some really interesting samples. So for example, we will, in the first case, we will take the phase and we are going to make it random. So all the phase information that was in this visualization is going to be random. The only thing that it will stay is these portions where the amplitude is higher. But this coherence that we see here, the pattern is going to be. So if we create the Fourier transform, where is the phase? We put random numbers there. You can see the formula is not so difficult. It's just that, random, uniform random numbers between 0 and 2 pi. No, is enough. And then we put this phi over here in the complex exponential. And then we have the magnitude of the Fourier transform and then the inverse. And finally, this sounds like this. So in a sense, for me, it's easy to understand this if we shuffle all the time structure of the original piece, but we stay with the color of the original piece. Let's hear the original one way more. So try to retain the color of this. How much lower and the type of the sounds they are there. And now we hear this. It's like the same palette of sounds, but all mixed up. There is no temporal structure. If you listen to some temporal structure, it's probably like that. An artifact, because we can randomize it many times and it's going to sound always the same. So this is really interesting because it's a way to see how important is the phase, because if we break it, we lose the temporal coherence of the music. And finally, another example with the phase manipulation. In this case, is instead of making it random, we will make it all fixed values. When we analyze a piece of audio, the phase values that we got have some structure. Some of these frequency components are going to be more like sine waves, more like cosine waves, or in between. But now we are going to put every frequency component with the same phase. So basically, if we generate a waveform with this, we will have a sound made only from cosines. So for example, at time 0, cosine of 0 is 1. So now all the components in the music will be 1 at 0. And then different frequencies will start moving, and sometimes they're going to sum up. They're going to be a constructive interference. Sometimes they're going to cancel. So here, the thing that I just mentioned, that the 0 value is summed up, it's not visualized because it's too high. And it's not normalized. Also, the numbers is not 1. What I said, this is not. The scale can be changed. But the thing is that the first part of the sound is so high. So I remove it. But then you can see these peaks they are there. That is when these cosine waves interference, make constructive interference. So this sounds like this. So now there is some temporal coherence. That thing was this. So this is really interesting because this process is also known as the autocorrelation function that is well used in signal processing to analyze signals. So we can still hear the rhythm. That's really interesting. But the notes or the original structure of the song is missing, but the rhythm is still there. And this process is really interesting to use it, to make it with different music examples. So if anyone has interest in this, it's really nice to try a lot of different musical examples. If you put jazz music, it has a lot of notes and no so much temporal, there is no that clear beat. You hear like a complete chaos of sounds. But if you put electronic music that is very basic, you got the results are really clear. So I'm not going to discuss this, but this is something I sometimes we work with in the class that is related with phase analysis also. And some reference, and that's it pretty much. Thank you.